This yellow box is a power transfer relay. There's two modes. One is the solar power through the inverter, and the second mode is the generator or outside power. This will switch over. Okay, you going?
Yeah.
External power comes in through the top, and this will energize the relay coil and switch it over to external power. If you disconnect this, the relay will fall back over onto battery power. I just want to show you a drawing of what's inside that box. The shadows are no good.
That's fine.
Okay. Here we have the outside power or the generator, and when that is powered up, it'll energize the coil and make these switches go into the lower position. And then you have the straight through outside power coming to those contacts when the armature is pulled down. So now you're seeing outside power at the output. This is distributed to all the loads in the trailer. Once the generator switches off, the relay coil is de-energized and it will go back to the shelf position of the armature, which means that the inverter output is now the active agent powering the trailer. Bed. This is our electrical system. This is our 3000 watt pure sine wave Go Power inverter, and it's run flawlessly. Underneath it is the lithium batteries, which aren't very visible. Over here you can see this is the BMS, or battery management system, for the lithium battery. This thing is a small computer which has a data communications line which goes to all the bridges going across the cells, and it measures temperature, voltages, and performs the equalization functions. Here is the rest of the board for the battery management system. And down here, this is a charge, and this is a discharge solenoid. And these will engage or disengage the way the computer says. Next we have the solar charge controller. This is an FM80 Outback. It's a lovely charge controller, very configurable. It's a maximum power point transfer type. Okay. Bloody bug. Outside of our lithium battery, we have an inverter. This is a 3000 watt pure sine wave inverter. The important thing is the pure sine wave part, because certain devices won't tolerate modified sine wave. The output of the inverter will go to our power transfer relay, and from there it goes out to our loads. Whenever there's no sunshine and we can't rely on solar, we use a generator. This is a Honda EU3000IS, and when this starts up, the transfer relay automatically switches the load to itself, and then it will continue to power the loads. Okay.
Okay.
Now on the load side of this lithium battery, this is where the inverter is. And the output of the benefit, what you want is a
Yeah.
It's, the wiring of the system. Sometimes you need heavy gauge wire, sometimes a lighter wire will be just as good. So let's take a look here. The voltage drop across a wire is equal to the current I times the resistance R. So if you have a high current, you get a higher voltage drop. So basically, for a given amount of power, the most efficient power transfer is done with the highest voltage possible. This is where the open circuit comes in. For the open circuit voltage comes in for what we have with the solar panels and what the Outback solar charger will tolerate on the input. So we want to run at 120 volts DC, which is a better power transfer than a lower voltage. So that's why we have the series parallel configuration. So given a power is equal to volts times amps. If the power is the same, you want to keep the amps as low as possible. That means the higher the voltage, the better the power transfer. On this rig here, we use 12 gauge wire because that's what was recommended by the manufacturer for the solar panels. What?
Is that 12 there?
What are you talking about?
The cable.
This is a basic sketch of this entire system in block form. The solar panels, which are monocrystalline, and they were provided by PV Power, which is based out of Chicago. These are the panels. There's panels 1, 2, and 3 are in series. 4, 5, and 6 are in series, and then they're paralleled. One thing we need to discuss is open circuit voltage. The open circuit voltage is the maximum voltage that a panel will produce.
And if you have a rainy day and you're running the
this
generator
is important
and you want to put
because
a
the
little bit of
Outback charge
in your battery,
controller
that will allow
has
it.
a specification which says the maximum open circuit voltage of the solar array can only be 150 volts. So on the safe end of that, 130 volts would be fine. These panels are 42 volts apiece.
This white box is basically
so
a battery charger.
42 times 3 is
And
120.
If you have a rainy day and you're running the
128
generator
volts.
and you want to put a little
And that's
bit of charge in your
paralleled
battery,
with another
that will allow it.
128 volts to double the current.
This
is what goes
the same
into
drawing
the
as we've
Outback.
looked at before, but with a
Little bit more
Now I wanted to
discuss. So here we have
the
3 solar cells
wiring.
in series. 3 solar cells in series,
As
both
we know,
parallel to each other, going to the input.
the voltage
of
drop
charge
across a
controller.
wire
We have high voltage,
E
therefore it's low current.
is
because
equal
it's
to
always
I
the same
times
power.
R.
High
So the
voltage,
more
low current
is going
there's a
through the
small
wire,
the higher the
resistance wiring
voltage
drop.
loss. So we can use thin wires on this circuit. Therefore we have better
Power
power transfer.
is equal to volts times amps.
On the other side of the charge controller, we're down to a low voltage.
So,
Because
we
the
can have
power is the
1,000
same on both
watts,
sides,
but if
and
we
the
have
voltage is
1,000
low on this
watts,
side, that means what with the current? The current is going to be high.
it would only be
If we have a
10
high
amps.
current draw going through the wire, remember the voltage
10 amps
E
of current flow
is equal
going
to
through the
I
wire
times
gives
R.
you a lower
And
voltage
this is
drop
a constant.
than if it was 100 amps.
In this case, we use thick wires. The thick, heavy gauge wires of the welding variety are the ones you want. And these connect to our inverter and to the battery. One more thing. The solar charge controller, what you need is one that's MPPT, which is maximum point power transfer. This means that the charge controller will go through a routine of trying out various loadings on the solar panel, and then it will figure out with its own computerization which loading gives you the most optimal power transfer. That's the most important thing. And the open circuit voltage. You must never have a higher voltage coming from the panels than the maximum open circuit voltage that the solar charge controller can take. Otherwise you'll pop the input transistors and then you can trash it. The battery, we're dealing with a lithium-ion battery in this case. Lithium-ion batteries have certain issues with them, and they have zero tolerance to overcharging or over-discharging. So therefore the batteries have to be hooked onto a controller or a battery management system. And this battery management system, in the very end of the process, it has the ability to either maintain contact with the batteries to the load or to disconnect the load or the charging. One more thing with the lithiums, if it has 100, let's say 100 ampere hours, that storage capacity you can use literally. You can use it from 0 to 100%. With lead acids, you can only use 50%. You only have 50% of the usable power. And around 12 volts, lead acid batteries should not be taken any lower. Because what happens is the plates will sulfate up, and you do that enough times and then it's difficult to clean them up again. What else have we got here? Our inverter, this goes to the power transfer relay, which I showed you, and the diagram. And from the power transfer relay, you can either intercept with the generator and an outside power source and just let the solar system idle, or you can have nothing connected to the transfer relay and the solar system will go straight through to the loads. Here we have the battery charger, and that also goes to the nodes directly. And with the battery charger, I plan to put in a voltage relay so that the voltage that the batteries build up to will never exceed 14.1 volts. That's the magical number for the Elite Power Solutions batteries. We will be showing a picture later on of what these batteries look like, but for now, the Elite Power Solution batteries, I forgot what I was going to say. So the various components of the power system for the trailer are all shown in this drawing here. We'll start going through it step by step. Here we have 6 monocrystalline solar panels, and we have 3 in series paralleled to another 3 in series. The reason for this, we have to explain open circuit voltage. The charge controller has a certain open circuit voltage maximum limit, and if you exceed that, the unit is essentially destroyed. So you have to stay below that value. For the Outback FM80, the open circuit voltage is 150 volts. So, in this case here, each of these panels is 42 volts. So we've got under 150 volts by quite a bit. So that gives us a little bit of a margin of error. At this point, I'd like to discuss the wire thicknesses required for the input circuit and compare it to the wire thicknesses of the output circuit. As you know, or might know, power in watts is equal to volts times amps. The voltage drop across the wire, is equal to amps times the resistance. Resistance is opposition to current flow. Now, if you can have, since that power is volts times amps, if you've got a high voltage, 120 volts DC, you're going to have a small current. If you've got a low voltage and the same power, in this case, you're going to have 10 times the amount of current. Because as current increases, the voltage drop across the wire increases. When we go into heavy loads or heavy currents, we must use thick gauge wire. In this case, you're talking basically welding cable, at least a 0 gauge. When we're up to the 120 volt mark, the solar panel input side, the voltage is 10 times higher, therefore the current is 10 times less, and we can get by on thinner wire. In this case, the manufacturer of the panels has already specified 12 gauge, so that's what we use. One last thing with these panels, they need to be mounted on the roof of the vehicle in such a manner that there's absolutely no shadows falling on the cells. A small shadow can reduce the power out by a significant amount, a lot, half, perhaps half. Getting onto the solar charger, this is the FM80 Outback, and that's the one we're using here. Continuing on, we have the battery. In our case, we're using a lithium-ion battery. In the lithium-ion battery, the circuit is a little bit more involved than with a lead acid. You have a charge solenoid and a load solenoid. You have a computer or a battery management system which monitors each cell with a bridge going across the terminals, and that's monitoring the voltage, the temperature, the balancing of the cells, whether they need to be balanced, and it will balance at the correct point in time. If there's any overcharging or over-discharging of the cells, or you're outside of the temperature range, these solenoids will be disconnected from the battery management system, and that will save the lithium-ion batteries. Lithium-ion batteries are unforgiving for overcharge and over-discharge. It causes permanent damage, and you will never be able to recover. Now, in the load circuit, we have, there's also 12 volts DC. The pump, the macerator pump, the water pump, some of the lighting run off the 12 volt circuit. And then we have the power inverter. Again, we're using super heavy gauge wire because we've only got 12 volts to play with. With 12 volts, we're dealing with high currents. When you have high currents, the voltage drop becomes very high as well. For the inverter, the most important thing that I would recommend is that you make sure you have a pure sine wave inverter. Some electronics will not work on modified sine wave. In the final 115 volts output to the loads, we have our own custom built, custom designed power transfer relay. If it's a rainy day and we don't have solar energy available, we might consider using a generator, such as a Honda EU3000 IS, which is electric start, and then this will switch the contacts of the power transfer relay and supply all the loads. If the generator isn't running, it's all taken over by the solar system. One more thing we use when we have rainy days and the batteries go low, we use a 60 amp charger. Basically, any constant currents at 60 amps will work with a lithium-ion battery, provided that there's a high voltage trip. And in this case, it's set to 14.10 volts. Once it reaches 14.10 volts, the 60 amp charger is taken off the batteries. We don't want the voltage to go any higher than that. Okay.